Okay. Namaste to all. I am Supriya Naika, your host for this session. Welcome to our 130th weekend talk on the extension of the periodic table. Creative is a combination of creativity and activeness. Together, creative. Knowledge Square, our tagline, sharing of knowledge doubles our knowledge. It's a pleasure to see so many like-minded individuals gathered here today, eager to engage in constructive discussion and broaden our understanding of this fascinating subject. As member of Creative, we are driven by curiosity and a passion for learning. Today's talk promises to enlightening our knowledge and explore possibility of extending the periodic table. We are honored to have the esteemed resource person, Dr. H.C. Manjunath, an expert in the field of physics. His wealth of knowledge and experience will undoubtedly enrich our discussion and provide valuable insight into this complex topic. I encourage all of you to actively participate in today's discussion, ask questions, and share your thoughts. Let's make this weekend talk a truly engaging and memorable experience. And catch the live stream on our YouTube channel, Creative GBD. Once again, I welcome one and all for today's session. And I call Chaitra, PG student, physics MSc student, Bangalore University, to introduce today's speaker. Over to Chaitra.
Yes, ma'am. Good afternoon to everyone. Myself, I am Chaitra, studying in MSc Physics in Bangalore University. Now, I like to introduce Dr. H.C. Manjunath sir. He is an Associated Professor of Physics in Government First Grade College, Devnalli, Bangalore, affiliated to Bangalore North University. He completed his MSc, MPhil and PhD. His research area are nuclear radiation, medical and health physics. He had 19 years research experience and 19 years teaching experience. He got many more awards in the research fields like Indian Association of Nuclear Chemists and Allied Scientists conferred the Dr. Tarun Datta Memorial Award in 2018 for the contributions in the field of nuclear and radiochemistry. He got gold medal and cash prize. And Karnataka State Council for Science and Technology and Government of Karnataka conferred the Sir C.V. Raman Young Scientist Award in 2021 for outstanding contributions in physical science, and he got 1 lakh cash prize and medal. And Vision Group of Science and Technology and Department of Science and Technology, Government of Karnataka conferred award for the outstanding research publications during 2022 and 23. And Vision Group of Science and Technology and Government of Karnataka conferred Seed Money to Young Scientist Award in 2013. And Indian Society for Radiation Physics conferred the Nucleonic Best Research Paper Award for the research paper entitled Bramstolong Does of Therapeutic Beta Nucleides in Bone and Muscle. Indian Association of Nuclear Chemists and Allied Scientists conferred the Best Research Paper Award for the research paper entitled A Study of Probable Alpha Ternary Fission Fragments of Thorium 257. Indian Nuclear Society confirmed the Best Oral Presentation Award during the Solid State Nuclear Track Detector and their applications. Best Poster Presentation Award for the research paper Projectile Target Combination to Synthesis UUE 295. Karnataka IND selected in the list of world's top 2% scientists in 2021 announced by the Stanford University and United States. He achieved world rank 432 among nuclear and particle physics scientists and 12th rank among Indian nuclear physics. He published 391 research papers in the national and the international journals and proceedings. He gave presentations and invited talks like lectures delivered that extension of periodic table and some theoretical tools used in the radiation physics and the material science and also radiation hazards. He guided 8 members for the completion of their PhD, and also currently he guiding 3 more people. He published some of the physics books and book chapters like a closer look at gamma rays, the study of photon interaction and parameters and dosimetric interest. And I'm proud that I'm a student of Dr. H.C. Manjunath sir in the Kolar. Thank you so much for giving this opportunity to introduce one of my best professor. Thank you so much, sir, and thank you, ma'am.
Thank you, Chaitra. Over to you, sir.
Yeah, very good afternoon. Thank you for your nice introduction. I think am I audible, right?
Yes, sir.
Yeah, thank you for your nice introduction, Chaitra. And first, I'd like to thank organizers for giving this opportunity to share the information regarding the work we did in last 7 8 years. Of course, I did my PhD in the radiation physics, that is the Bremsstrahlung radiations and all these things. After that, I shifted to the nuclear physics and then the fabrication of this nanomaterials, that is anti-cancer drug, all these things. So here the most basic things today I'm going to explain. That is the cumulative results of the our research. Of course, I know some of you audience are coming, MSc students and physics background, chemistry background. I'll try to explain as simple as possible. Right now, periodic table. So and the super heavy elements, all these things. As this first slide shows, that is what the screen of our work, the periodic table. So the important point is the variation of the variation of the proton number with the neutron number that decides the stability of the element. So that is why of course, today I'm going to explain this thing, periodic table. What is periodic table? How the people are trying to extend the periodic table, all these things. So, and also thank to the Srinath sir who gave this opportunity to share the information among the different. This is the a typical platform. So, yeah, my talk goes like this. Actually, I have planned like this. So just I will give a brief introduction about the periodic table. What is the periodic table? How this periodic table comes? All these things, and what is the way of extending the periodic table? How the different people are to the extent of periodic table, and why the many experiments were filed to extend the periodic table, and then what is the reason for that failure experiments, and again, and what is our role in the extending the periodic table. That all these things I'm consolidated, I'm going to explain in this a short information. First, come to the meaning of the periodic table. A systematic arrangements of the elements according to their atomic number. According to their atomic number, electronic configuration, recurring chemical properties. That is the periodic table means. So the element means, it starts from the hydrogen to the now today we have the upper limit for the periodic table is the ignition. Ignition, and the lower limit is the hydrogen atom. Hydrogen atom to the ignition atom. Hydrogen element to the the ignition element is the thing. So what is if you define in a simple way, an element is what macroscopic. This is the definition, of course, the macroscopical definition that cannot be broken into the simpler substance. Of course, the atom again we can define. I can split into the nucleus, again nucleus into quarks, all these things. Macroscopically, the element is defined like this, that cannot be broken into the simpler substance. Hydrogen, carbon, sodium, each element is having its own chemical properties, physical properties, so appearance, shining, all these things, different properties are there. It's very difficult task to arrange the elements in a systematic manner. In the first time, that is what in 1829, Dobereiner first framed the periodic table. The concept of the periodic table, officially formed by this Dobereiner. So this is called Dobereiner's triads. Triads means three elements were grouped together such a way that atomic mass of the middle element is the average of the first and last. For example, if you see here, lithium is there and the potassium is there. If you add the atomic mass of the lithium and the potassium and divide by 2, that gives the 23. The 23 is the actually atomic mass of the sodium. That is how the first he formulated. But unfortunately, afterwards, many elements were discovered so that they failed to accommodate in a triads manner. For example, if you take this nitrogen and AS, so here the middle atomic mass average of the two becomes 44.45. That is not the atomic mass of the P. We can say this triads, Dobreiner's triads rule, failed to present all the elements in a systematic manner. Even though it is a first attempt and beginning idea of the arrangement of different elements in this thing. The second idea about the periodic table comes from the John Newlands. This is called octaves model. This was proposed in the 1865. Octaves means 8 elements, right? These 8 elements are arranged in a systematic manner according to their increasing order of the atomic mass. So it's, here hydrogen to the here increasing order of this platinum, increasing order of their atomic masses. So it is almost looks like the music notes, and that's why it's called Newlands octaves actually. After that, later several new elements like the molybdenum, osmium, radium, different elements were discovered. Later on, they were not able to accommodate all the atoms in like this. That's why this is the second failure of framing the periodic table. Afterwards, in 1869, by this time, 63 elements were discovered. And this Dmitry Mendeleev believed that atomic mass is the most fundamental property in classifying the elements. So he arranged based on their atomic masses, and in that table, in the Dmitry's periodic table, 7 rows were there. Those are called as the periods. 8 columns are there. Those are called as the groups. And the beauty of this periodic table is at the center, some blank spaces were kept. So these vacant spaces were for the elements that were yet to be discovered. So, and before that only he named that elements as eka boron, eka aluminum, eka silicon. After once these elements like this helium, neon, xenon were discovered, so those elements were systematically placed in that gaps without disturbing the position of the other elements. So that is the success of the first success of the framing the all elements in a systematic manner. So this Mendeleev's periodic table based on the Mendeleev's law. This Mendeleev's law says that the physical and the chemical properties of the elements are the periodic function of their atomic masses. Of course, later on this periodic table needs some correction. The main drawback of this periodic table is, Mendeleev's periodic table is, no fixed position could be given to the hydrogen in the table as it resembles like alkali metals as well as the halogens. At certain places, an element of higher atomic mass has before an element of lower atomic mass. For example, if we take the cobalt, whose atomic mass is 58.93, it comes first, and the nickel is having the atomic mass of 58.71, it comes afterwards. That is the one drawback of this Mendeleev's periodic table. It needs the correction. So again in 1913, this Henry Moseley corrected that, and he formulated the periodic table. And this periodic table is based on the modern periodic law. This modern periodic law says that chemical and physical properties of the elements are the periodic function of their atomic number rather than the atomic mass. So Dimitri believed that this chemical and physical properties were depends on the atomic mass. So he corrected that. He said that this chemical and physical properties of the elements are the periodic function of the atomic number. Based on that, he arranged all 103 elements in a systematic manner, and he kept some blank spaces for the elements which were yet to be discovered. And this period now this periodic table is using. This periodic table is, as I said, based on the modern periodic law. So this is what a chart, what I represented in this slide is the periodic table published by the IUPAC. This IUPAC is it's a body which publishes the periodic table in every year. If any element were discovered, so that should be included by IUPAC only. So this is the periodic table. As I said, the hydrogen is the lower limit, ignition is the upper limit. So usually the elements whose atomic numbers greater than the 89 and less than the 103, those were called as actinides. However, the elements whose atomic number are greater than 103 are called as super heavy elements. So these elements are synthetic elements, means these are not naturally occurring in the nature. For example, the elements whose atomic number is greater than 95, these elements were discovered, synthesized through the fusion reactions. Different types of the fusion reactions are there. So here, like that, these super heavy elements are also synthesized through the fusion reactions. There are two kinds of the fusion reactions were used in the synthesizing the periodic super heavy elements. That is the cold fusion reaction is the one, and the hot fusion reaction is the second one. So it depends on the targets. So usually fusion means a projectile is made to hit on the target, fused together, combines to form a compound nucleus. That compound nucleus is, if it is survives against the fission, then that is considered as the stable element. Here, based on the targets, if it is a target is a lead or the bismuth, then that type of the fission is called as the cold fusion. So up to the elements 113 were synthesized through the cold fusion, the cold fusion reaction. However, these cold fusion reactions were failed to synthesize the elements whose atomic number is greater than the 113. Then the concept of the hot fusion comes. In the hot fusion reactions, excitation energy is more. That means we need to use the more and more energy for the projectile, and that fast moving calcium beam, usually calcium projectile is used in this fusion reaction. Fast moving calcium beams are made to hit on the actinide targets. They fuse together, forms the compound nucleus and survives against the fission process, nuclear fission process, and having the, of course, the lifetimes from the minutes to the, of course, the milliseconds. So today, up to the 118 elements were discovered, and that is, posted in the periodic table. As I said, the upper end of the periodic table is the 118. So now the attempts were going on to synthesize the 119th element and 120th element. So here, so if you see the radioactivity, as I said, the extension of periodic table is linked to the radioactivity. So if you see the chronological order of the radioactivity periods between 1896 to the 1940, that period is called as radioactive period. So here the polonium was discovered and radium was discovered. Again, this radon, protoactinium, francium, all these elements were discovered between the period of 1896 to the 1940. Marie Curie, she was the first person who started to synthesize the elements through this fusion reaction, through this chemical approach or physical approach. After that, between the 1940 to 1952, that is called as neutron period. So some of the elements were discovered through this neutron techniques. So that is the 94 element was discovered, 96 discovered, berkelium, californium was discovered. And again, between that is almost 70 years back, that is from 1952 to 1974, the super heavy elements were synthesized through the light projectiles and also through this cold fusion reactions. So here in the year 1981, super heavy element 107 was discovered, and again this 1982, this meitnerium 109 was discovered. This is a chart what I represented in slide. This slide is the chronological order of the how these different elements were discovered in various labs. So those elements were called as agnesian, again this tennessine, all these things. It based on the name of this element is based on the place where that element were discovered, and also sometimes it based on the researcher who is going to discover that element. That also matters here. So this is the time, time chart how these elements up to the 118 were discovered. If I listed out the reactions, fusion, as I said, the elements beyond this 95 were discovered through the fusion reactions. So Rutherfordium, whose atomic number is 104, this is synthesized through the fusion of the plutonium and neon, and again the dibnium, and again the seaborgium, flerovium, livermorium, are these are synthesized through the various fusion reactions. So this is what the JNR is the one important nuclear laboratory which were actively involved in the synthesizing the elements, actively involving extension of this periodic table. Japanese also involved in the extending the periodic table. Japanese added one element, that is the nihonium, so whose atomic number is 113, and they synthesized through the fusion of the zinc and the bismuth. The joint collaboration of the Russians and Americans, they were synthesized the 115th element, 117th element, and last agnesian element, that is in the year 2006. After that, this experiment was repeated, of course. So, as I said, the various labs like the USA Berkeley lab is involved in the synthesizing the element. This Russia Dubna accelerator is also involved, GSI, Darmstadt, and the Riken lab of this Japanese, Ganil of the France. All these famous nuclear laboratories were involved in the extension of periodic table by fusing the elements. So after this, why these nuclear physics persons are very much interested about the synthesizing the new elements, why these persons are very much interested in the extending the periodic table. As I said, today's limit for periodic table is 118. Now the people are trying to search for 119, 120. Why these people are searching that? One theory says that is the theory of island of stability. This theory of island of stability says that if the isotopes is having the neutron magic number, then its half-lives will be little higher than that of the neighboring isotopes. That is the the theory of the island of stability. That means, so here an artistic chart is shown here. So that the maroon color, the hills represents the most stable one. So here at the top left, there is a lead comes here, most stable element. As we move towards the downwards, so in the upper end, almost near to the 126 and 120, there's one more maroon color element. That means the most stable element we can found, and that is why the people were searching to synthesize those elements. People are focusing up to the extending the periodic table up to the 126, and the theoretical microscopic theory says that. So here element 126, 124, and 114 were found to be most stable, and the periodic table may extend up to that one. Now this is the charts, the microscopic theory results. The red color hot region, the red color represents the the region where that nuclei is found to be most stable nuclei. That is why the experimentalists are very much interested to extend the periodic table. Just if you analyze how many elements there can be in the nature. Till now, as I said, the synthesis of the element 118 is the present limit of experiment. Whatever we talk up to the 118, 120, 126, all these things, that is the hypothetical elements. But the experimental limit is 118. There is a constraint on the availability of the suitable projectile target combination for the production of 119 and 120. If you see this figure, the first layer of this shows the cross section. Cross section means number of atoms per reaction. You know, as this atomic number increases, this cross section goes on decreases. Now it comes in the picobar, means if you do the experiment around 15 days, we'll get a 1 or 2 counts. That much difficulty is there to synthesize this one. And also second layer of this figure shows the fission barrier. As this atomic number of the element goes on increases, fission barrier goes on decreases. That means as the fission barrier is very small, there is a tendency to split the heavy element into the smaller fragments. That is why it is difficult to survive the element against the fission as the atomic number goes on increases. And the third layer shows the half-life. So when it comes to 104, it comes in the thousands of seconds. When it comes to 118, it comes almost in the 1 millisecond. That is why it is very difficult to detect that also, because the element 118 is having the lifetime of the millisecond. And also many theories says that in spite of that, the theoretical evidence is there. This relativistic atomic many-body quantum theory says that the elements can extend up to the 172. Bohr's atomic model also strongly says that the periodic table can extend up to the 137. And most precise, this quantum electrodynamic theory also says that there is a chances to extend the periodic table up to the 170. That is why the people were struggling to synthesize this, extend the periodic table. So in this slide, I just show the, the experimental attempts to synthesize this super heavy element, means experimental attempts to extend the periodic table. The one experimental attempt, that is the first, in GSI lab. So using the fusion of the titanium and berkelium, they tried to synthesize the element 119. So of course they did a 2 times they repeated experiments for about 6 months. They didn't get the even a single atom. And also continuous 90 days experiment was conducted in RECON through the fusion reaction of vanadium and curium. Again they failed to discover the element 119. Again in JNR also, Russia, again they tried to synthesize the element 120 through the iron and the plutonium reaction. That is the continuous 120 days experiment. They didn't got even single atom. Again, the same thing happens at GSI of Germany and the Ganilla of the US also. Many experimental, almost 9 to 10 experimental attempts were there. But huge effort has been put up since 2009 to the till now, but they didn't got the results. So what is the reason for the failure of these experiments? So that is in that direction we did a lot of work. Of course, we revealed the secret behind why those experiments were failed to synthesize the new element. Before going into that, I just explained the mechanism of the synthesizing the new element. So as I said here, this is a projectile. This fast moving projectile is made to hit on the target. So again, before the forming of the compound nucleus, there are 2 stages. One is the capture stage, another one is the pre-capture stage. So in the pre-capture stage itself, there is a chances to undergo a fission that is called as, of course, Coulomb fission. As once this pre-capture stage survives against the Coulomb fission, it enters to the next stage called the capture stage. Here also there is a chances to undergo one more type of the fission called quasi-fission. Again, once this capture nuclei survives against the quasi-fission, then only it forms the compound nucleus. So this compound nucleus, this again there is a chances to undergo one more type of the fission called fusion fission. So again, if this compound nucleus survives against that fusion fission, then it forms the evaporation residue that is called as a new element is formed now, right? That means to form a super heavy element, three types of the fission is the threads. One is the Coulomb fission, another one is the quasi fission, another one is a fusion fission. In that direction, we try to reveal the secret of the fission happening during the fusion reactions. So we try to reveal the decay width of the fission. So and we explained that we how that fission depends on the projectile target combination also, and of course we predicted the possible projectile target combination. So what we did is as I said, the periodic table between 104 to the 118. So this almost 15 elements. We clearly, analyzed these 15 experiments, and we formulated the 5 rules. Now it is, that is called as rules of thumb for synthesizing this periodic table. What is that rules of thumb says? It says the shape of the nuclei also. So 5 rules are there. First rule is fusion of 2 spherical nuclei yields the larger cross section. Second rule says fusion of one partner among the projectile target nucleus is a spherical, then it yields the cross section in the picobar. That means 10 to the power of minus 12 bar. Third one, fusion of 2 deformed nuclei cannot produce the measurable cross section. Fourth one is deformed evaporation residue nuclei yields the better survival probability. And last one says about, so we need to select the suitable energy for the fusion. So most of those 8-9 experiments, they failed in selecting the proper energy for creating the new element. So these are called as what the rules of thumb for synthesizing the super heavy elements. So in this direction, we formulated our own model, and we first validated using the available experiments. And again, we predicted the cross sections, and it agrees well with the experiments. And as I said, and we clearly explained the reason why those experiments were failed. For example, as I said, this vanadium and curium, these were first attempted in the JNR of this Russia. They conducted the experiment at 241 MeV, and there the cross section is very, very less. If you shift the energy to the little smaller, that is around 230, there is a chances to get the larger cross section. There is a chances to synthesize the new elements, and that is reported in the scientific journals. And the one important success of our research work is what this optimal energy rule we proposed. Based on that, these Americans were repeated the experiment. Of course, this super heavy element, this 115 were discovered in the 2004 at the energy 42.7 MeV. At that time, they were getting the cross section of 2.49 picobar. Later on, after our optimal energy rule, they repeated the experiment and they reduced the energy to the 34 MeV. At that time, they got the cross section around 34.2. I mean, 10 times larger than the previous experiment. We can call this is one of the success of our rule, what we framed to extend the periodic table. And if you see the second proof for that extension of that optimal energy rule, again, in 1996, this element 112 was discovered in the American labs at 41 MeV. At that time, they got only very small cross section, 0.9 picobar, and after optimal energy rule concept, again they repeated the experiment and they got the cross section around 3 picobar. And similar thing, same thing happens in case of the 114th element also. People were accepting our rule, adapting our rule. They tried to synthesize the new elements. So as I said, the formation of the compound nucleus is very, very important during the fusion reaction. That plays very important role in the synthesis of the new elements. In that direction, we clearly formulated an empirical model, an empirical formula to calculate the compound nucleus formation probability for any kind of projectile target combination. And that is also reported in the international journals. Again, the once that is compound nucleus is formed, the survival probability is also very important. So that survival of the compound nucleus against the 3 kinds of the fusion is very important. that we explained very well, and we framed a very simple empirical formula, and that is the that now the people are using to calculate the survival probability of the given projectile target combination to synthesize the new elements, and that is also reported in the international journals. And we studied that there is a systematic variation of the compound nucleus formation probability as this atomic number of the projectile and target goes on increases, and that is also reported. Of course, details are not explained here, but and again, we considered that deformation. That means the shape of the nuclei is very important. Atomic number of the projectile is important. Atomic number of the target is important. And again, the shape of the nuclei is important to synthesize the new element, to create the new element. That is explored in the scientific platforms. And again, this regarding now the people are very much curious to create the element 120 in Japanese as well as Japanese labs as well as the Americans. They are trying to synthesize the element 120 because this is the focusing element in the island of the stability. For that, we clearly explored which projectile is suitable and which energy is exactly suitable for the creating this new elements. And again, this is the nuclide chart. Of course, we propose from our groups. This yellow color gives the the nuclei which can undergo the cluster decay, and this again this maroon color nuclei undergoes this alpha decay, and again this cyan color beta plus decay. This nucleate chart we published from our own group, the Polar Physical Research Group. What we are doing here is, so from our group we published this nucleate chart up to the super heavy element. We extended the periodic table. And when it comes to the super heavy element 117 and 118, 119, we have given the suitable projectile target combination to synthesize those elements, systematically studied at what energy the survival probability is maximum, at what energy this compound nucleus probability is maximum, and what are the probable isotopes for the super heavy element 119 or 120. Of course, this slide is very important. You can call this is one of the success of our research work. As I said, this Japanese in the Riken lab, they are trying to synthesize the 119 element and 120th element, and they adapted our optimal energy rule as well as the thumb rules, and they quoted our research paper, and they gave the theoretical evidence from our research paper, and they started doing the experiment. They are going to synthesize the super heavy element 119 and 120 using the projectile target combination what we proposed in our work. Of course, this is the PPT presentation given by the director of the Riken lab of this Japan. Of course, they are going to synthesize the element 119 or 120 by the end of 2024. So this is our contribution, of course, to the super heavy element 120, 121, 122, 123. We have provided of course, a lot of theoretical evidence for the existence of the new isotopes of the super heavy elements, and again the you can say different isotopes of the elements from the 119 to the 126 that we published in the various international platforms, of course. So here, coming to the summary of my talk. So we theoretically identified the super elements from 117 to 126. That means according to our group, periodic table can be extended up to the 126. And we selected the suitable projectile target combination to synthesize those elements. And again, so our research aim is, as many Americans added 2 elements to this thing. The Japanese also added the 1 element. Again, this Russians added 9 elements to periodic table, and again this Germans also added the 4 elements to this periodic table. We aim to synthesize at least 1 super heavy element among this 120, 122, 24, 26. So that the discovery credit should come on the name of the Indians. That is of course the aim of our research. In this direction, we're trying to conduct the experiment. The problem with the experiment is in India, we don't have the sufficient projectiles. We contacted with the IUAC people. Of course, we last time also I sent the projectile, I mean the proposal to the IUAC. So again, because of the lack of the facilities, so they refused. Of course, next year that IUAC people, they're going to start the one more accelerator beam. So that beam definitely will help us to conduct the experiment. Will, of course, I have the confidence to succeed in this synthesizing new element like 119 and 120. So okay, so this is the collaborators Sabha and again the RP Singh, Tapan Nandi. So thank you very much for your patience. Of course, I know I didn't went for the deep into the technical points. So now I most welcome for your suggestions, questions, comments.
Thank
Am
you,
I
sir.
audible now?
Yes, sir. Yes, sir. Thank you.
Yeah.
It's open for question session. If any questions, please communicate here. Any questions? You can unmute and you can ask the questions. Sir, one question in chat box.
Yeah, chat box. Yes. Let's see. 3. One is. Thanks for okay. Yes. From her name is Shrika, right? Shrika GS.
Yes, sir.
She is asking where you will carry out the experiment. Where you will carry out the experiment. So good question. That till now what we did is the theoretical studies. So we are doing some sort of experimental theory. Means there are 3 kinds of the theories are there. One is the fully theory that is based on the theoretical things. That is, you can say microscopic theories and macroscopic theories. But here we are formulating the theory based on the available experiments. That is the one new direction. Experimental theory is the experimental theory, and now whatever we are explaining here is the theoretical results only. We are saying that the periodic table can be extended up to the 126. Okay, but it must be confirmed through the experiments. So that is why we are trying. We are, as I said, we submitted a proposal to almost 6 months back. I submitted a proposal to the IUAC. Unfortunately, the energy of those beams are not available. So that IUAC will install the new accelerator facility at the end of 2024. By the time, hopefully, we'll get the accelerator facility. Once that accelerator facility is available, hopefully we'll success in creating the new element and we'll add it to the periodic table. Srinath sir, am I audible?
Yes, sir.
Sir, can you comment on the work, sir? Srinath sir. Okay. So, of course, ನಾನು ತುಂಬಾ ಡೀಪ್ ಆಗಿ ಹೋಗಿಲ್ಲ ಅಂತ, ಐ ಮೀನ್ ಟೆಕ್ನಿಕಲ್ ಆಸ್ಪೆಕ್ಟ್ಸ್ ಜಾಸ್ತಿ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಿಲ್ಲ ಅಂತ ಅನ್ಕೊಂಡಿದ್ದೀನಿ. I hope you will convince with my presentation.
Hello.
Yes, sir.
Can I ask a few questions?
Yeah, please, sir. Please, sir. Please.
One question is, have you noticed any regularity between the lifetime of the heavier elements
Yes, sir.
and the Z number, atomic number? Is there any regularity have you found or have you predicted anything?
Yeah, it's a very good question, sir. Actually, there is a one law in the literature that is a well-known law, Giger-Nuttall law. more than the 20 empirical formulae were available, which can represent the lifetime and the decay energy as and the atomic number, of course. But all those 20 laws were not in 20 empirical formulas were not included the deformations. As I said, atomic number is also very important. Energy released also very important. The literature ignores one more fact, that is the shape of the nuclei. So now, of course, we did in that direction. We included the shape of the nuclei also. These three factors: energy released during the decay, alpha decay, and atomic number of the nuclei, and as well as that is the shape of the nuclei. These three are important parameters which can decide the lifetimes, because all these super heavy elements were decays through the alpha decay, sir.
One more thing, you mentioned about a few processes during your presentation. One of them is the so-called cold fusion, and
Yes,
the
sir.
second one is quasi-fission. Can you explain what they are with examples? What do you mean by cold fusion and quasi-fission, please?
Okay, right, sir, right, sir. First one is I'll just the terms I'll pronounce it. That is a cold fusion, sir. FUSION, fusion.
Yeah, cold fusion. Yeah, that's what I meant. Yeah, cold
And
fusion.
second one is fission process, FI, splitting.
Quasi-fission. What is quasi-fission?
Yeah, the cold fusion is, usually if the lead and the bismuth were used in a fusion reaction, so the low energy is enough to fuse. I mean, the barrier is very less because of this magicity and shell structures. That is why the nuclear physicists, they used to call that fusion process as cold fusion. Quasi-fission is the splitting of the compound nucleus, splitting of the pre-capture before forming the compound nucleus. That is one kind of fission, sir, not.
Yeah, fission only, but I've not heard of quasi-fission. I've heard of the usual fission.
Yeah, there are three kinds, sir. Quasi-fission. Quasi-fission is there, fast fusion is there, Coulomb fission is there. So that is the fission which occurs before forming the compound nucleus.
Oh, before forming the compound nucleus.
Before forming the compound nucleus, sir.
Okay. Thank you.
Yes, sir. Thank you, sir. Any more questions, sir?
Sir, one more question in chat box. One more.
That is very good afternoon and great. That is excellent. Okay.
The word super is used. Why the word super is used in sheet?
Yeah. I'll come to that. Usually, element between the element whose atomic number between the 89 to the 103, those are called as the heavy elements or actinides. The element trans uranium, we used to call that is whose atomic number is greater than, that is much more heavy. That is why that is called as super heavy. There is no particular meaning. Much more heavier than heavy elements, super heavy elements. Of course, the Indian the thing is the Indian science is not progress in the direction of the nuclear physics. The accelerator facility we have only one, that too in the North India, right? So those North Indian people, they will not easily allow the South Indian people to conduct the experiments. That is actually what I observed. There is a parity, North Indians, South Indians, like that. So we badly need of one nuclear accelerator facility in South India. That is, of course, important for the progress in nuclear physics.
Any more questions?
Optimal energy. One question is there, Madhu.
Yes.
Madhu. Okay. Optimal energy predicts fusion cross section. Which relates the half-life half-lives of super heavy element. Excellent. Which relates the okay, right. I'm not getting the which relate. Yeah, optimal energy is what the energy at which the two nuclei fuse together and produces the larger cross section. That is the optimal energy. If that is we'll get a large cross section. But half-life is what it relates to the decay process, whether it undergoes the alpha decay or the cluster decay, like that. Okay, one more question they're asking. I have one question using the same process. So can we synthesize the very good question. Can we synthesize the elements like AU, AG and plat? Absolutely, but it is through the nuclear techniques. We can synthesize that. So, but the converting that into the bulk is difficult. Atoms we can synthesize AU, but in the bulk amount it's difficult. One person is asking, Shrika, which softwares are required to do the theoretical studies? I agree with you, right? Theoretical softwares, usually using the theoretical softwares and doing the something is not that much great work. So we should analyze the experiments thoroughly. That is a very important thing. We should study the experiments. After that, we should frame our own empirical model. That is the important thing. Based on the experiments, we are not using any, of course, some codes, nuclear codes we are using, like that is used in Fortran codes, but that is not that much important. What is important is based on the experiments, we formulated the empirical models. That empirical model produces the values close to the experiment. Why? Because it is based on the experiments. Softwares is not that much important. Of course, we produced from our group, we have given the more than 40 empirical formula. Anybody can calculate the cross section. Anybody can calculate the half-lives through the simple inputs of atomic numbers, mass numbers, all these things. That you can convert it into softwares. Not at all an issue. Yeah. Any more?
Sir, one more question, sir. Anita ma'am, you can unmute and you can ask the question. I have given permission. Unmute yourself and you can ask directly.
Hello, sir. Hello.
Sir, you are muted.
Hello.
1 minute, ma'am. Sir will
Okay.
talk with you.
Audible, madam? Now audible?
Yes, sir. Yes, sir. You can.
Yes.
Sir, it was an excellent talk, sir.
Thank you.
May I know what inspired you to explore in the field of super heavy element, because it is too large field and it is quite difficult to produce all such things. May I know your what inspiration that you have gained from to explore this, sir?
Yeah. Thank you, madam. The Madam Curie synthesized the element curium, right? At that time, Curie, she was not aware of the applications of this curium, right? But here also, the inspiration for our work is, we were first involved in the fusion reactions. Later on, we came to know that the fusion of some nuclei is yielding the larger cross section. So after that, why don't we adapt those fusion reactions for extending the periodic table? In that direction, we extended the work. That's why we are doing. So of course, in the supernova, in most of this astronomical phenomena, also this super heavy elements. There is a literature reports. These super heavy elements were observed in the supernova explosion. There is a literature reports. Now the people were connecting. Now here we are trying to create the new element through the accelerator. So literature says that some super heavy elements which were already there in the supernova. So in that direction also work is going on. That is a nuclear astrophysics. Some people are doing in that work also.
Thank you so much, sir. May 120 element be named after you, sir. We wish for that. Thank you, sir.
Thank you, madam.
Rikar, sir, if you want to talk with sir, you can unmute yourself and you can ask. Shrika. Okay. Okay, sir. Sir, you are muted. Unmute yourself and you can ask. Shrika. Okay. 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 Shrika. Okay Any more questions? Okay. I think no more questions.
Yes, madam. Yeah. Shall I conclude, madam?
Sir, tell me about your awards, sir. That C.V. Raman Young Scientist Award. You give some background of that, sir.
That is based on some research the papers what we published based on the government of Karnataka. Government of Karnataka has declared that based on the publications what we have.
Okay. Thank you, sir.
Yeah.
Okay.
Yeah. Yeah. Thank you very much for giving this opportunity to share the, our, results with the, this reactive platform, right?
Yes, sir.
And also I thank to the Srinath sir, who gave this chance to explore this information among this audience. So thank you very much, madam. Thank you.
Thank you, sir, for accepting our invitation and for being with us. It's a very pleasure to have you on Creactive. Thank you, sir.